final speaker for the session, which is Alicia.
Yes, sure.
Hi, Alicia.
Hi, I'll try to share my screen now.
We've got it. Yeah, so
okay.
Our final speaker is Alicia Gressent from INERIS in France. And so delighted to have Alicia here today to tell us about data fusion for air quality this time. Thanks, Alicia.
Yeah, thank you very much, Claire. It's a pleasure for me to present our work today on data fusions for air quality mapping. We use local sensor observations to do that. Local sensors can be used for various applications. The most important ones are mainly the monitoring of air quality by using fixed sensors or very small stations. We use sensors for public awareness, but also individual exposure assessment. The sensors data can be used for the improvement of the sensor systems. They can be used for the improvement of the emissions inventories of air pollutants, and also for the modeling of these pollutant concentrations. We also would like to use these sensors for the redesign of the regulatory air quality monitoring network. And to actually serve these different applications, we use an essential tool, which is the air quality mapping. So I will focus the following of my presentation on air quality mapping, and in particular at the urban scale. So there are lots of challenges to use this sensor observations for air quality mapping. The first important one is the representativeness of these observations, depending on the support and the sampling plan. There are also the heterogeneities of the data sets in time and space. Because data can miss in space and in time. And I think that the most important ones is the uncertainties of the measurements, because if you want to use this sensor observations in the regulatory framework, we need to correct the bias of these measurements, and to consider the uncertainty in our data fusion procedure. So let's now just have a look at the different approaches that are used for the data fusions based on these sensor observations. So land use regression models are actually used for data fusions with the sensors, so that are multilinear regressions between pollutant concentrations measured by the sensors and some predictive variables. So here, this is an example for PM 2.5 concentration, so fine particulate matters concentrations in Seoul, in South Korea. Other statistical approaches like machine learning or deep learning approaches are also used. So here, this is an example for carbon monoxide concentrations in Sydney in Australia. Then we have also Bayesian approach that consider uncertainties related to the model and the measurements. So the data fusions propose an update of these concentrations values. And here, this is an example with the blue approach. So the best linear unbiased estimators, this is based on Kalman-Filter approach. And you can see an example for the NO2 concentrations in Grenoble in France. And the last family of approaches that I wanted to present today is the geostatistical approach, so for the kriging. I'm going to give you some more details about kriging, because this is the method we use for our data fusion procedure with the sensor observation. So here, this is just an example for NO2 concentrations in Oslo, in Norway. And I'm going to detail this kriging approach in the following. So in the framework of the French Central Laboratory for Air Quality Monitoring, we have developed the CSAM tool. CSAM is actually a tool for combining sensor observations and dispersion modeling estimates at the urban scale. Okay, I don't know if the animation is working well, but anyway. The CSAM tool is based on the based on the kriging with an external drift, with a weighting of the sensor observations depending on two different parameters. The first one is the data dispersion at each measurement locations and the measurement uncertainty. So we use these two different information to define the variance of measurement error, which is then used in the kriging procedure. So we did an application in Nantes, French city, and we published this work in Environment International 2 years ago now. And I'm going to present this in details. Yes. So you can see here the Nantes map with the different station, the reference station of measurements that are in the top left, the upper left panel, and on the upper right panel, this is the positions of the reference, sorry, the fixed sensors that we used. The fixed sensors are from Atmotrack that actually provided the fixed sensors and the mobile sensors observation of PM10 concentration. So you have the trajectory of the mobile sensors on the bottom left. Here you can see the different color that corresponds to the different sensor IDs that are in different vehicles, like ambulances, service vehicles. And then you can see on the bottom right the density of the measurements in the Nantes city. So you can see that the density is very heterogeneous depending on the sampling. We don't have actually the control on the sampling, so we have to deal with this heterogeneities in time and space of the sensor measurement, as I mentioned before, as a challenge for the data fusion. So what we did an analysis and a pre-processing of the sensors data. So this is for November 2018. We estimated the variance of the measurement error. As I said, it's a parameter that we use in the kriging procedure and that allows to weight the sensor observations in our data fusion. And so we applied the kriging with an external drift. This is the universal kriging based on the fixed and the mobile PM10 sensor observations. And also the results of a dispersion model, which is the ADMS-Urban calculation. So first we made a pre-processing of the sensor data because when we compared actually the sensor observations and the different data at the reference measurement station, we can see that we have differences in the distribution of the data. We identified two different potential effects. The first one is the algorithm effects, and the second one is the particle size effect. So we wanted to correct for this bias. And for this, we proposed two different steps. The first one is to eliminate the sensor data which are below a threshold, which is based on a repeatability criterion, which is calculated here based on pollution, which are 3 periods of pollution actually. And then the second step, we corrected the observation, the sensor observation, by the daily variation of the background concentration, which is actually determined based on the reference station. And we obtain a data set which is corrected, and we can see here that we have a distribution which is more similar between the sensors and the reference stations. And we actually use this corrected data set for the data fusion procedure. Our data fusion procedure, as I mentioned, is based on kriging. So this kriging is an estimate that considers the observed values, but also the information on their positions. And this is also based on the main concept of spatial continuity. So two observations located close to each other should on average be more similar than two distant observations. So here you can see the example of the X1 observation that will be actually more similar to X2 than X3. And in our case, the pollutant concentration fields that we want to estimate is a random process with a realization, Zx, of the random variable in X. And this is described by a variogram, which is the semi-variance of the increase depending on the distance between the two positions, the 2 points. And here you can see on the left an example of what is a variogram. So you can see this is here defined by nugget effects, the seal and the range, and it's depending on the distance between the couple of points. In our case, we are in a non-stationary framework, so the realization, the expectation of the realization is unknown and it varies in space. And for a concentration Y at a location S0, this concentration is actually the combination of the expectation drift, which is explained by a linear relation of auxiliary variables and a random process. And in this study, we chose to use output from dispersion model simulation as an auxiliary variable. So we use the ADMS 2016 average of PM10 concentrations as a drift for this kriging procedure. And we define, as I mentioned, the variance of measurement error, the VME, that is the combination of the dispersion of the observations at each position, measurement position, and the uncertainty. In the uncertainty term, we have the constant relative uncertainty of type. This is defined as 50% for fixed sensor observations and 75% for mobile sensor observations. So we assume that the uncertainty for mobile observation is higher than for fixed sensor observations. And that definition relies on the European directive and the analysis we did at the beginning of this study. So I think that the main challenge here is actually to define more accurately this uncertainty. This is here a relative uncertainty, but if we want to be more accurate and to increase the performance of the kriging, we have to actually define more accurately this uncertainty in the data fusions. But this is actually a first. Yeah, this is the first test with this VME. So we have to, in the future work, to try to do something better. Anyway, we did this kriging using the 2016 annual mean of the pollutant concentration based on ADMS-Urban estimations. We did the estimation at the hourly resolution from 7 a.m. to 7 p.m. for a particular day of November 2018. So it was the 29th of November. And the spatial resolution of the output grid is 7 meters. So here, this is an example for the kriging application. So you can see on the upper panels, the model estimation of PM10 on the background with the observations of the sensors that are average for the hour. So this is for a particular hour at 7 a.m. So this is on the, on the left, this is the observations, and on the right, this is the associated variance of measurement error that we have calculated. So the kriging is then based on the variogram of the residuals that is calculated based on the observations and the model, the dispersion model. You can see that the correlation between the observations and the model is not so good. This is mainly because of, I think, the choice of the drift, because we chose an annual mean. We are actually testing this by using other time resolution, like the hourly mean of the model output to improve this, and also because some bias can actually remain on the sensor observations. The correction that we applied did not correct the whole bias on the observations, and that could be also explained by the impact of the mobility on the observation that we did not correct here in this work. So by applying this kriging based on the diagram of the residuals here, we actually obtain this kind of fuse map here on the bottom left. And I also put the sensor observations in the top just to see the difference between the fuse map and the observations. And you can see the kriging standard deviation, so the kriging error in the bottom right. So if we just look at the results for the whole day, we can see that we have the data fusion results are very different depending on the time of day. So in fact, for certain hours, we have local hotspots, which are noticeable because of few sensors data point with very high or very low PM10 concentrations associated with a low variance of measurement error. And also for this particular error, we have a correlations between data point and the dispersion model, which is not very fully satisfactory. For other hours, so 7 a.m., 9 a.m., and 10 a.m., we can see that we don't have this kind of hotspot. This is mainly because we have more data points that are with high or low PM10 concentrations, with low variance of measurement error, and also the correlations between the points, the data points, and the dispersion model is quite better. And for other hours, at 5 p.m., 6 p.m., and 7 p.m., the correlation between the data and the drift, so the dispersion model is negative. So for those hours, we admitted that this is the estimations are not relevant at all. We compared also the daily mean of the concentration at the reference stations. We have here 5 reference stations, and the daily mean of the data fusion. So we can see that the data fusion estimates is closer to the reference measurements, but we actually smoothed the pollution peaks. So this is better in average, but for very high events of pollution with PM10, high PM10 concentrations, we don't have a good representation of this particular event. We also just, we have tested the impact of the uncertainties. So the relative uncertainty that we used, that was 50% for fixed sensors and 75% for mobile sensors. So we try to change this uncertainty to be 25% for both, or 100% for fixed sensors and 150% for mobile sensors. We can see that the lower the measurement uncertainty, the greater the weight of the sensor data in the estimate, and the better the performance of the data fusion. So we actually need to quantify accurately the measurement uncertainty, as I mentioned before, associated with the sensors, and especially regarding the mobility. So we are now working strongly on trying to estimate the impact of the mobility and the meaning of the measurement with this mobility features. Some conclusions. So we can say that data fusion is very, with sensor data, is very promising to produce air quality maps at the urban scales, even if there is still some issues that need to be addressed. In this work, we actually we try to in the future, we try to develop new methodologies for outliers detections, also to derive the drift of the sensors. We are also working on different data fusion methodologies. So we try to use other geostatistical approaches like numerical variogram, spatiotemporal kriging, stochastic partial derivative equations. So we are working on this. I just want also to say that we work within the FAIRMOD group, the Forum for Air Quality Mapping, and in particular in the low-cost sensor subgroup. So we work for a benchmark on methodologies to integrate low-cost sensor network with official measurements to improve air quality maps. So the idea is at a higher scale. So here, this is at national scale. We used fixed sensors to try to improve the map, the air quality map. So we compare the different methodology that each country has developed for network calibration and data fusion. So I won't go in details, I think. But yeah, we just try to adjust our SESAM tool at this national scale, and by using corrected data from a sensor network here. So I think I'm done for this presentation. Thank you very much for your attention, and don't hesitate to go to the GitHub and try to test this data fusion code with your own data and share your results or your questions on this. So we'll be very happy to answer your questions if you have questions on data fusions. Thank you very much.
Thank you very much, Alicia, for a really interesting and great presentation. So yes, as Alicia said, if you have any questions at all, feel free to raise your hand or to put your question in the chat and we can ask that question to Alicia. Alicia, just while everyone's thinking, there was just a couple of things that I was thinking about. The kriging approach that you're using here, is it spatio-temporal kriging or is it spatial at time point?
It's spatial at time point. It's not spatial temporal kriging. This is something that we tried actually. We did not publish on this, so we are still testing some other kriging or geostatistical approach in general to try to compare with this. But yeah, it's spatial kriging, and yeah, we tried spatial temporal kriging with we did not publish these results for the moment. So.
Okay,
yeah.
Great. Yeah, so presumably with that, then you don't have any kind of computational challenges, but with the spatio-temporal, I guess there might be more computational issues with because your data are quite high resolution in time in particular.
Yeah, you're right. That we have. So what we did here is the hourly average of the observations. But you are right that for sensor observations, we can actually have observations every like 10 minutes. So yeah, we have to think about how to consider these observations. What is the best way to integrate this kind of observations, and also maybe there is no. Yeah, because of the uncertainty of these observations, maybe the average over the hour is a good thing to do. But if you want to use mobile observations, there is like it's not a good idea to do the average because we lost kind of informations if we do that. And there is also this issue of calculation resources, and we have to think about this. And yeah, it's it's not so easy. Yeah.
Sure. And people that you will work with will want a quick answer as well, I'm sure. Yeah. We've been in this kind of context, we've been exploring fixed rank kriging a little bit, and there's a spatio-temporal version there. I'm not sure if that's something that you've looked at all, and it might not work with what you're trying to do, but I say we've just started exploring that in a couple of similar kind of data fusion projects that we've got at the moment.
Okay, interesting. Yeah, I did not test this, but interesting. Yeah, thank you. Okay.
I don't see any other hands or comments or questions just now, unless there's anything I'm missing. So if anyone has questions for Alicia, feel free to put them in the chat. And I'll just finish this session just now by thanking all of our speakers. So thank you very much, Alicia. Thank you very much, Alejandro. Thank you very much, Xiaoyu, for a really interesting session. I've really enjoyed it. So thank you for speaking for us today. And I'll pass over now to the next session. Thank you, everybody.